Hello, my name is Bridget. In this video, my group and I will present our project for the computer programming subject. Our project consists of two systems, the Smart Traffic Management System and the Waste Management and Recycling System. Our first project, the Smart Traffic Management Systems, aims to reduce traffic congestion and ensure smoother traffic flow on the roads. With this project, we strive to help people save time and reduce fuel consumption while also minimizing air pollution and urban stress. Next, we have the waste management and recycling system. This project focuses on reducing waste and promoting sustainability. It also encourages people to adopt recycling as part of their daily life, aligning with modern advancements and environmental goals. In conclusion, the goal of our project is to use Python programming to develop innovative and sustainable systems for a smarter and more environmentally friendly future. This is our first project, the Smart Traffic Management System. It uses real-time data from sensors and cameras to detect vehicle movement, analyze traffic conditions, and recommend the best routes for drivers, optimizing travel time and reducing environmental impact. This is the flowchart for the Smart Traffic Management System. It illustrates how the system operates using Python programming. The process begins by collecting the number of vehicles on the road at each junction. Next, the system processes the traffic data to adjust the signal timings accordingly. After that, it prompts the user to input the current weather conditions and any road obstructions. Finally, based on the weather, obstructions, and all the gathered data, the system determines the best route for the drivers.
Just a brief overview of the pseudocode for this program. We will start off with to start the program. Then we initialize the list of junctions. Third, we collect the real-time traffic data. Fourth, we adjust the signal timings dynamically based on the traffic data. Fifth, we collect weather and obstruction conditions. Sixth, we determine the optimal route based on traffic data, weather and obstruction. 7 will be to display the results, and 8 is to end the program. Now we'll go over the formulas involved in this program. So first is to determine the levels of traffic congestion. So we have high level, which is 60 cars and above, which makes the signal timing to 100 seconds. Then we have moderate level, which is 41 cars to 60 cars, which makes our signal timing to 70 seconds. And we have low levels of congestion, which about 40 cars and below, which makes signal timing to 45 seconds. Then second, we have determine the optimal route, which sorts out the traffic data according to the values and the data obtained from the traffic congestion. It will exclude any junction that is affected by the weather condition or road obstructions. So I'll briefly go over the code for the program due to a lack of time. So we first have the three main functions, which are data collection, which captures traffic flow at every junction using the user's input. The second function will be dynamic signal timing, adjusts signal durations based on congestion, high congestion, medium congestion, and low congestion. And third, we have optimal route suggestions. It recommends the routes based on the congestion, weather, and obstruction conditions, which avoids specific functions if there are any obstruction or it's raining. So we have the program flow. Firstly, will be to collect the traffic data, which is the input vehicles count per junction. Second will be to adjust signal, then dynamic timing based on the traffic data. And third will be the route suggestion, which filters the routes based on the conditions. So this is an example of our code running. So we first input the number of cars. So at junction 1 we have 10, junction 2 we have 8, 3 we have 6, and 4 we have 5. So all the signal timings will be adjusted to 45 seconds. And then now we check for the weather. It is sunny, and the road obstruction, there's none. So it will determine that junction 4 is the most optimal, followed by 3, 2, and 1. Now I'll briefly go over the limitations of this program. So firstly, we have weather and obstruction handling. We only allow junction 4 and 2 for weather and obstruction handling, but this is unrealistic. So to improve this, we can allow real-time data about affected areas and dynamically calculate detours. Secondly, there's no error handling. We can't check for vehicle counts, weather, or obstruction responses. So it could lead to runtime errors if there's invalid inputs. To improve this, we can add an input validation or error handling for robustness. Lastly is an inefficient data entry. So the system requires a manual input. This is very impractical for real-life situations. So we can integrate IoT sensors which can collect real-time data automatically from junctions, cameras, and sensors.
Our second problem is waste sorting and recycling system. Our product description is to effectively sort out domestic waste from recyclable items. This could help reduce the amount of waste products that would be dumped into landfills, as well as to reduce costs of producing new materials by recycling used items. We're designing a system to help classify types of waste and to optimize the recycling process for improving sustainability efforts. We're going to do 4 codes. The first code is for waste recognition, which is through image using AI modes. The second code is to track amounts of waste and recycling capacities needed to create an optimized collection route. Third is for coding to schedule waste pickup based on data of collected waste. The final code is for obtaining efficiency of recycling and how it impacts environment and cost reduction. This is our complete solution. This flowchart represents a structured process for waste management and recycling optimization. It starts by taking the type of waste, for example, paper, glass, metal, plastic, or organic, and its quantity as inputs. The input is validated to ensure it's numeric and non-negative. If invalid, the process loops back to re-enter the data. Once valid data for all waste categories is entered, the system calculates and displays total waste quantities. The predicted recycling capacity is estimated by adding a 20% buffer to account for potential variations. The waste data is then sorted in descending order based on quantities to prioritize handling. Collection routes are optimized for efficiency, followed by calculating environmental impact reduction using predefined efficiency factors. The process concludes with a summary of results, including total waste, recycling capacity, waste reduction, and overall efficiency percentage. For our pseudocode, there are 12 steps. We begin with starting the program. Second is to prompt the user to input the type of waste, for an example like paper, glass, and organic waste. Third would be to prompt the user to input the quantity of waste for the selected types. Next would be to check if the input is valid. We would do that to verify if the input waste quantity is numeric and non-negative. If the input is valid, we would proceed to the next step. If it is invalid, we would loop back and prompt the user to re-enter the waste quantity. Next, we would repeat steps 2 till 4 for all waste categories, for example, the remaining metal, plastic, and organic. Next would be to display waste quantities for each category and calculate total waste by summing up quantities of all waste categories. Then we would add a 20% buffer to the total waste to predict the recycling capacity. And then we would sort the waste categories by the quantity of waste in descending order to prioritize collection. Next, we would optimize the collection routes based on the sorted waste data, and we would prioritize high quantity waste for earlier collection. And then we would calculate the reduction in environmental impact based on efficiency factors, for an example like energy saved, carbon emissions reduced, etc. 11th step would be to display a summary of the results, including total waste, recycling capacity, including buffer, waste reduction, and efficiency percentage. And then we would end the program. The formulas in the waste sorting and recycling system calculate key metrics such as total waste by summing waste quantities, sort waste by quantity to prioritize collection, and to predict recycling capacity by adding a 20% buffer, and to calculate environmental impact reduction based on recycling efficiency factors. The system also computes total recycling capacity and total waste reduction by summing the required capacities and reductions, respectively. Finally, recycling efficiency is measured as the percentage of total waste successfully recycled, ensuring optimized and effective waste management. For the program code, the code starts by defining the types of waste categories, which is paper, glass, organic, metal, and plastic waste. The user input function is the first interaction with the user where they are prompted to enter the quantities for each waste type in kilograms. The function ensures that the input is numeric and non-negative using a loop that only exits when valid data is entered. If the users entered invalid or negative values, they are asked to correct them. This step is crucial because it ensures that only valid data is processed by the program. The function stores these quantities in a list for further processing. For sorting the waste data, once the waste quantities have been collected, the program proceeds to the sorting phase. The sort waste data function pairs each waste type with its corresponding quantity. It then sorts these pairs in descending orders based on the quantity, ensuring that the waste types with the most significant quantities are prioritized for collection. This sorting logic is implemented using a nested loop to compare quantities and rearrange them. This sorted list would help in optimizing the collection routes and determining which categories need attention first for recycling. After sorting the data for the recycling capacity prediction and the route optimization, the program calculates the predicted recycling capacity for each waste type by adding a 20% buffer to the quantities to ensure that the system is prepared for any unexpected increases in waste volume. The predict recycling capacity function computes this by multiplying each waste quantity by 1.2 and rounding the result. It then prints out the recycling capacity needed for each type of waste. Next, the program optimizes the collection route through the optimize collection routes function, which uses the sorted waste data to prioritize the collection of the waste categories that have the largest quantities first. This ensures that the program addresses the highest volume waste types before moving on to the less significant ones, thereby improving efficiency in collection operations.
This function calculates the environmental impact of recycling using the calculate environmental impact function. Each waste type has an associated reduction factor that represents the efficiency of recycling for that category. For example, recycling paper might reduce the waste by 80%, while metal might have a 90% reduction factor. The function multiplies the waste quantity by these reduction factors to calculate the amount of waste saved from landfills for each category. After calculating the reduction for each waste type, the program provides a final summary, including the total waste collected, the total predicted recycling capacity needed, and the total waste reduction achieved through recycling. It also calculates the overall recycling efficiency by dividing the total reduction by the total waste and multiplying by 100 to get a percentage. This efficiency percentage shows how effective the recycling system is in reducing waste and promoting sustainability. 5 kg is needed for the predicted recycling capabilities. The optimized waste collection route is to collect paper first, followed by glass, metal, plastic, organics with 4 kg respectively. The environmental impact reduction is the paper is reduced by 3 kg, glass reduced by 3 kg, metal is reduced by 4 kg, plastics reduced by 3 kg, and organic reduced by 3 kg. To summarize the report, the total waste collected is 20 kg, the total predicted recycling capacity needed is 25 kg, and the total waste reduction from recycling is 16 kg, and the recycling efficiency is 80%. Next is limitation. The first limitation for the problem is the manual input dependency. The program requires the user to manually input waste quantities, which can lead to errors or inefficiencies. And automating data collection, for example, sensors or file input, would improve usability. The second limitation is the limited error handling. The code only checks for non-numeric or negative inputs. Other inputs errors, for example, empty inputs, are not handled. Additional validation for incorrect or missing data would improve robustness. The third one is the scalability issues. The system is suitable for small-scale scenarios but lacks support for large waste management operation. And incorporating modular code architecture and scaling features would allow for integration into larger systems. Conclusion. Our project focused on developing 2 technology-driven solutions to address societal challenges. The smart traffic management system adapts to real-time traffic conditions using data from cameras and sensors, reducing congestion, travel time, fuel consumption, and harmful emissions. The waste management and recycling system optimizes waste sorting and recycling to promote sustainability by reducing landfill waste, conserving raw materials, and lowering production costs. This solution demonstrates the potential of programming and modern technologies to address real-world challenges and lay the foundation for the future advancements in smart system.